Hello, everyone, and welcome to my talk about drone control or controlling a drone using Rust. My name is Lachezar Lechev. I know it's hard to pronounce or remember, so don't worry if you get it wrong or forget it. I'm from Bulgaria and I'm currently working at ADEX during the day. I'm using Rust for the last 1.5 years. Yay! And it's full-time job. So this was my dream only 2 years ago, and I finally achieved it. Our work is centered around the Ethereum network Ethereum blockchain at the moment, and we are building a display ad network for reduced ad fraud and increased user privacy. At night, however, I play around the Rust working group that we have started at the beginning of this year. And the goal is to help and push the open source community into the growing aerospace industry by providing information, materials, tools, crates, and etc. to the industry itself and to hobbyists, of course. One of the main reasons that I wanted to start this working group was, in fact, that I couldn't find enough information at a reasonable level that I can understand. At my job and at the working group, I make and build open source projects. I love to travel a lot, and combined with the fact that I'm location independent, it's awesome. However, due to the current outbreak, traveling is not a certain thing anymore. Combined with traveling, I love to go to festivals and parties. I especially like trance music. After all, we have to blow off some steam somehow from time to time, apart from being software engineers and developers. As you can also see, I'm a heavy user of emojis as well. They're part of me, and I just like it. Today, we're going to take a look at the Parrot Anafi 4K drone. The company Parrot makes a bunch of drones. Some of them fly, some of them don't. Initially, when the whole project started, Ignition, one of the other co-founders of Rust, started hacking on a different drone. It is called the Jumping Sumo, and it's a remote-controlled two-wheeler that can also jump. However, we, as in I, thought it would be awesome if we make it work for the flying drones and try to control them. The picture you see here is one of the packages that the Parrot company has of the Anafi 4K drone. It includes the Sky controller as well that you can use to control the drone. It is good time to mention that none of this is sponsored by them in any means, at least not for now. It is an accessible small drone, especially because of the price, and it's easy to work with. And why did we choose it in the first place? Well, we chose it because it has a lot of features, including Wi-Fi over which you control the drone. The drone has its own network that you can connect to. It has a 4K camera, and the Parrot company provides a C SDK to be used for the drones. It's open sourced, and it's the main way we find many of the things that we need in order to hack on the drone using Rust. The company provides other SDKs as well for building Android and iOS apps. They also include a Python version, but it's using the C SDK. And that's where the other SDK, PyParrot, comes into play. PyParrot is a Python SDK, and it's very, very helpful when things don't work and you wonder why. There is a simulation tool called Sphinx. It has many features that I haven't reviewed or used yet. However, since I don't actually own an AFI 4K drone, it's very useful to play around with it and build the Rust SDK with it. There is also the Free Flight app, which is for iOS and Android, that gives you the ability to connect to any Parrot drone, and you can use it even for the simulation. I tried it one day, but that's not what we are here for. We want to use Rust to control it. There is the Skies controller that I already mentioned, and the list of features goes on. Now that we know what we are working with, it's time to take a look at how does it work. The main point, it all has to do actually with communication. And the way we communicate with the drone is over Wi-Fi, the same way as the apps and the Sky controller. The Sky controller is to your phone. It has its own separate Wi-Fi antennas and stuff. And I think that the phone is used for the video stream itself instead of on controlling the drone. And regarding the connection and the communication, we need to talk about three main points. The first one is the handshake. After connecting to the Wi-Fi of the drone, we need to establish communication between our controller, that is our program, and the drone. The Parrot drones use their own protocol that we are going to take a look at. It includes different mechanisms and things that we are still finding out how to work with. And the protocol uses what we call frames. And we'll see what they look like and represent in a bit. This is all incorporated in the AR SDK ARS crate, which is in heavy development stage right now, aka work in progress. And now let's start with the handshake. After we have connected to the drone over Wi-Fi, we need to establish the connection between our program, aka the controller, and the drone. Each drone has its own initial port. It's usually 44444, and we use TCP and make sure that we handle the handshake correctly, especially the response from the drone. Through the established TCP connection, we send a request, which is serialized with Saturday and Saturday JSON into a JSON string. It includes the D2C port, which means drone to controller port, alongside the controller name and type, which I'm not really sure how the drone uses. And there are other ports for the video streams, which I haven't bothered to check yet. After sending the request, we should get a response in JSON, which we deserialize again with Saturday and Saturday JSON. We get a controller to drone port from the drone and its response, which is basically how the controller will speak to the drone. It also includes a status field, and if the status field is 0, then we have a connection. Otherwise, we need to try the handshake again. The response provides other fields as well regarding other options, ports, etc. We currently don't use them, and honestly, at this point, I don't know what they are for yet. And by this, we have a connection. Hooray! And to get a visual representation of what I just explained, I've included the request logs here that you can see. And we use the same 44444 port to connect the drone and send the request to the drone, as well as the field we send to it. And finally, we have the successful response from the drone. Again, you can see the controller to drone port and the status fields, as well as the other fields that the drone sends. And now that we have this connection with the drone established, it's time to talk about the protocol. The protocol uses what we call frames. And the first part of the protocol is the ping pong frames / mechanism. Then we have the listener that listens to the provided drone to controller port for incoming from the drone messages and frames and deserializes them. Then finally, we have the command sender, which we will use to send frames to control the drone. The ping pong frames and mechanism in a nutshell means that the drone sends us a ping frame with some gibberish data, which I actually found out a couple of days ago. Before that, I thought it also combines an actual frame. However, this is not the case. It's just gibberish. And the drone expects a response of that ping frame called pong, which we will see how it works when we talk about the frames themselves. The pong frame should contain the same data, the same gibberish data that was received from the ping. And if we don't send any pong response in 7 seconds, the drone usually disconnects the controller, as in our program, and we need to do the whole handshake again. The listener at this point does some basic stuff which are crucial to the communication, the connection itself, and debugging and so on. It uses a UDP socket with the controller to drone port that was provided by the drone during the handshake. And each received message can contain more than one frame. And we will see how we cope with this and extract each frame from the message. The listener also deserializes all known and unknown frames. Since it's still work in progress, not all frame deserialization is implemented. And this gives us an easy way to gradually decode each frame, either by using the C or the PyParrot SDKs and looking into them and trying to understand what each byte means. At this point, the listener is handling ping responses by sending a new pong frame to the command sender so that it can also be sent to the drone, as well as the so-called acknowledge frames, which we'll get to in a bit, which we'll get to it in a bit. I've also included some logs from the listener to better understand what's happening. As we can see, we receive some bytes from the drone, and then we see the deserialized version of the parsed bytes. We are going to take a look at each individual element in a bit. On the other hand, the command sender handles the sending of frames from our program to the drone. It uses UDP socket as well, and we expect it to send frames from the controller to the drone on the drone to controller port. This is the same port that we have provided on the request when making the handshake. Right now, it sends the raw bytes to the drone. The actual serialization is happening on a different place. And the logging, again, it's straightforward. This example is for the takeoff frame, which will tell the Anafi 4K drone how to magically take off and hover above the ground, waiting for further frames and commands. The earlier logs that we saw from the listener were actually the acknowledge response from the drone for the takeoff frame that we saw in the previous slide. Basically, it is saying that it received the frame and executed it. In order to fully understand and know what each thing means, we need to take out the frames. And as we mentioned before, we can receive more than one frame from the drone. And the way we distinguish between every frame, like shown here, is the way the frame and its bytes are arranged. I've personally found that it's easier to understand the frame by representing the bytes as U8 or unsigned 8-bit numbers. And this message can roughly be translated to this. The first frame we can decode has a type data, which means that it's a frame containing some data. The buffer ID is pink, and following the buffer ID, we have the sequence ID. This sequence ID is based on each individual buffer ID, and it starts from 0. When the count gets to the limit of U8, it overflows and starts from 0 again. This way, we can send an acknowledge frame to confirm to the drone that we've received a specific frame. But we can also make sure that the drone returns an acknowledge frame that guarantees us that a command we sent is executed. For example, we might want to know if the drone has actually landed and executed the landing command. Otherwise, it can still hover over the surface. The next 4 bytes, or U32 in a nutshell, is the length of the full frame. It is serialized using Little-endian, or the less significant byte first. The length includes the headers, type, buffer, sequence ID, each represented by 1 byte. The U32 that the length represents, this is 4 bytes, and the feature length of the frame, if there is one. And by this length, we can split each and every individual frame if we have received more than one. In similar matter, we can decode the second frame, and as in the first one. And the type here is data with acknowledge, which means that the drone requires us to send and acknowledge for this frame, meaning that we need to confirm that we have received it. Then we have the buffer ID DC event, which means drone to controller event. And this is an event that the drone sends us to notify us about something happening. In this case, it's sending us a calibration state that the drone is into. And as we saw in the previous slide, the message had 35 bytes. And we can see that the length of the first frame is 23, and the length of the second one is 12, which is a total of 35 bytes. And with the current implemented types, this looks like so. To elaborate a bit on the whole buffer ID and sequence ID, you can see that the pink frame has a sequence ID 1, and the DC event also has a sequence ID of 1. Each buffer ID has its own counter. The next time we receive a pink frame, it should be with a sequence of 2. The same goes for the frames that we are sending. As you can also see, not all types are currently implemented and defined. And although the pink, in the pink frame, we see that the feature is unknown, and with the value of 3, this is not used since it's part of the gibberish data of pink and not an actual feature value. Now, let's take a look at the type and the buffer ID. The type basically means that what type of frame we have, what kind. As we can see, we have acknowledge data. Most of them are easy to understand, but some of them we still don't know how to use, or we haven't looked at them. On the other side, we see the buffer ID. They are usually separated in 2 distinct categories. From the drone to the controller, they are usually prefixed with DC, not all. The pink and the acknowledge from sent with acknowledge, the last one, they are not prefixed yet. And we can see that the punk is also not prefixed, and it's part of the controller to drone buffer IDs. These are the buffer IDs that we're going to use to send frames to the drone. And we already saw the DC event in action when we took a look at the calibration state example from the previous slide. Now that we know at least what the headers do and what the frame looks like and represents, it's now time to take a look at the frame itself and build a whole frame, which we can use to send to the drone. The frame struct is pretty simple and straightforward. The bulk of the work, however, is in the features. Those features represent each and every command, event, setting, state, etc. that the drone understands. Some features include only simple values that we saw in the previous example. Some of the features include C-strings and special parsing, like, for example, the setting the date and time of the drone. Even the frame for sending piloting commands to the drone includes a timestamp that is specially encoded, that is in a specific format, let's say, and we need to parse it for both serialization and deserialization. It is important to mention, though, that when we are serializing the frame, we serialize the feature first of the frame, and then we can calculate the total length of the frame in bytes. When we have the total length, we can encode it at the right bytes in order for the frame to be fully ready to be sent to the drone. As we saw in the messages example, it's usually like the third byte to the 7 or something like that. For the actual serialization and deserialization of the frames, we are using the crate scroll. This means that for each struct or enum, we have to implement try into context and try from context, which gives us the ability to serialize and deserialize the bytes, as we saw earlier. This does require a lot of research and boilerplate at this point in order to map every single feature that we can have. And this is why we still have a lot to implement and track down in order to finish the whole serialization and deserialization of frames. Now, I was going to show you a GIF of a working example. However, let's see how the gods of live demo, if they're going to allow me to show it live to you instead of actual GIF. So first we need to start the Sphinx tool. It's pretty simple command. It does steal your Wi-Fi card because it needs to create the same Wi-Fi as in the drone. It uses the same firmware as the drone, and it also includes this .drone file that has some settings you can tweak and the 3D model and stuff like that. When we started, it's going to give us this gazebo UI, and we can see the drone right here in the middle. Maybe I can, And if I rotate it, we can see the camera here. So it's pointing at the back right now. For reference, we can insert a 3D model of some building, an apartment building. And usually there is a video stream of the drone. However, because I don't have a dedicated GPU, I'm not sure if it's going to work very well. It usually doesn't. It gets to the initial view of the webcam, of the camera actually, and then it doesn't update until the drone has landed. However, let's try it and see if it works. So we have the drone here. I have this example for taking off with the drone, and I should take off, hover for a couple of seconds, then it should fly up and down and land. As we can see here, the logs that I showed earlier with all the frames and the actual drone now moving and accepting the commands we're sending. Let's try the video. Nope, the video is broken, so I'll just close it. And we can see that we're currently sending the takedown command. And now we've just sent the landing command. And the drone has landed successfully. The drone is we're still keeping the connection with the drone, and it's still sending some information. although it has landed, and we can still start it up again very easily if we send another takeoff command. And thankfully this worked. Yay! Demo time, yes. Oops. This is still work in progress, pretty much. And we have a long way to go. However, it was really fun to build this, and we are exploring new things that we can make and do with the drone. I've been in contact, for example, with the Rust Computer Vision working group, and I hope we can make some post-processing of the video from the drone. We still have a lot of flying to do, especially to figure out what is a good approach for the API to make it easier, more idiomatic to use, and to control the drone and each aspect of the flying itself. There are, of course, much improvements. It's just hacking at this point and trying to make things work. There are definitely improvements to be made, especially separating the frames by receiving frames and sending frames to make it more comfortable to work with them and build the correct frames instead of sending something that the drone won't understand. And some of the other mechanisms that I haven't mentioned here, especially around the flying and sending the commands and receiving outputs of them or confirmations. We still have a lot of implementations to do. All the features we need to be able to distinguish between the receiving and the sending because when we receive an unknown frame and we don't know how to handle it, this can crash the drone, and we should know all the correct values for that. I hope this whole experience is inspiring because we had a lot of fun building it, especially thanks to Ignition, who started the whole journey, starting with the small jumping sumo, and then I just, hey, let's try the flying drone. We had a lot of frustration. Why doesn't it work? What's broken? Why does it disconnect? However, with enough time and with enough when you want to do something and you want it really hard, you can achieve it. It's just a matter of time. And this project is part of the Aero Rust working group. You can find the SDK repository below, as well as some other cool projects we are working on in our GitHub repository and organization. I've provided some links to some of the Parrot tools, as well as the Rust Computer Vision organization, if you're interested in that. And thank you for your time. Oh, okay, perfect. Oh, a couple of slides. Sorry. I'm open for questions, so please share them on whatever streaming portal you're looking this at. Question on Twitch. RP Ruiz. Sorry if I missed this at the beginning, but is this an OS project? Anyway, one can collaborate. Yes, the software is free and open source right now, and I have provided you in the last slide with the actual repository that you can get involved into. Just jumping into the Discord server, ask questions. There are a lot of people there, especially people with backgrounds in whatever. They're aerospace engineers and material engineers. We have separate, separate groups of people working on different projects in different areas. Okay, another question. YouTube. Zbigniew. Oh, sorry. Zbigniew Siciarz. Would it be possible to run Rust flight controller software directly on the drone without the network round trip? Yeah, I haven't checked that. Probably it might be possible to flash some custom firmware on it, but at this point we're still playing with Wi-Fi. Question on Twitch, Exakage. Do you welcome contributors without much experience? Yes, we do. The whole point of the Rust community, not only a working group, we are a whole community, is to share knowledge and information on various topics about aerospace and engineering and whatever, space even. So it's definitely encouraging to see new people coming in and trying to bring them up to speed or try to help them find their place. Well, other questions? Maybe I can return the slides that we've missed. YouTube, Boris, Tiran, is there interest in space industry to use Rust? Yes, there is. There is quite a big interest right now, especially in the Rust community, as far as I know. On another conference on Oxidize, they were talking about how they want to bring the Rust and to verify the compiler, or at least part of it, to be used in space, because there are really tight things that they have, like verification of the tools. Each tool must be verified that it does what it's meant to be, and it's defined somehow. Question, YouTube. Michael Lazowski. Have you tried to write it in other languages? For example, C or C++? No, I'm mainly working with Rust nowadays, and I don't even know C and C++ a lot. However, the main SDK is actually in C, so it might be interesting to take a look at it. Okay. Okay. So I need to pick somebody with the most interesting question. I definitely like questions about Rust, because the main idea is to share information. And although I don't know anything about drones or space, I can actually go somewhere and ask somebody and start preparing myself even for a career there. So in that case, I would like to Okay, Twitch, another question. Final question, okay. Final Spartan. Won't we need to have a compiler purely made from Rust before we can verify it? Targeting LLVM would be heartache to verify. If I remember correctly, we don't need pure Rust compiler to do so. There are subsets of the C or C++ compilers that are verified, as far as I know. And we can do the same thing for Rust, especially given that we now have two backends or frontends, keep forgetting, with CraneLift. We can take a subset of Rust and try to verify it bit by bit until we can start using it in space applications. And as I said, I do like questions regarding Rust. So I would say X say cage. I choose you. Best question. Yeah, from Twitch. So thank you, everybody. Sorry, I'm a bit nervous talking in front of people. However, it was really fun, and I hope you had some inspirational things that you found in my talk. Bye bye.
All right. Hello, everyone around the world. Thank you so much for having me today here at Rusty Days. It is late afternoon here in Seattle, Washington, but I hope whatever time it is in your part of the world, you are doing well. When I work with someone who is just learning Rust, they sometimes question whether the Rust borrow checker is their friend or their foe. One second, I'm getting delayed audio for some reason. All right, we're having some technical difficulties here. Let me fix this. One moment. Alrighty, folks, for some reason I was getting some delayed audio there in my headphones. So what I'm going to do is just take the headphones off and continue the presentation. So I apologize for this. Let's go ahead and go back to the beginning. When I work with someone who is just learning Rust, they sometimes question whether the Rust borrow checker is their friend or their foe. If you take a look at the Rust subreddit, you will see it was common to see posts like this. Newbie question regarding the borrow checker. Help fighting the borrow checker. And does it ever get easier fighting with the borrow checker? So it's common to feel a lot of frustration when you're first starting with Rust. However, as I watch people get more experience in Rust, they tend to come around to the borrow checker and realize what it is protecting them from doing. So in answer to the question, is the borrow checker a friend or a foe? I say the borrow checker becomes your friend through gaining experience with it. And along with getting experience, it's also very helpful to understand how it works and why it does the things it does. We're going to dive very deep into that, but before we do, let's briefly cover who I am. I'm Nell Shamrell Harrington. I am a senior staff research engineer at Mozilla. If my voice sounds familiar to you, I am the lead editor of This Week in Rust and host of the This Week in Rust podcast on the Rustation station. If you ever want to get in touch with me, honestly, Twitter is the best. Go ahead and tweet me at @NellShamrell. And let's get back to the presentation. First, just to set expectations, we're going to take an overview of the Rust compiler. In order to understand the context in which the borrow checker works, it's important to understand a little bit about how the Rust compiler works. And then we will dive very deep into the borrow checker after. So let's start with that overview of the Rust compiler. Let's take a look at this code example. This Rust function declares a vector composed of the integers 1, 2, 3, 4, and 5. And after it declares this vector, it then uses a for loop to iterate through each integer in the vector and print it out on a new line. Now, if I were to run this using cargo run, I would see these 5 numbers, 1 through 5, printed out on the screen. Now, this seems pretty simple, Cargo builds and runs this piece of code for us, but there's a lot that happens underneath the surface in the compiler when Cargo is building it. There are 5 general stages to compiling a piece of code. It starts with lexical analysis of the code, then parsing of the code, semantic analysis of the code. This is where the borrow checker comes in. And one moment, I'm getting a message. Looks like we're having some problems with the slides. Let me go back a little bit. All right, I'm not sure why the slides are not updating, but we are going to figure that out right here. And we're going to get this figured out for you folks. Give us just a moment. What I'm going to do is I'm going to stop presenting for a moment, and then I will restart presenting just to see if that fixes the issue with the slides not updating. One moment, please. And let's do this again. All right, I think this should fix the issue. One moment. Let me see if the slides are updating on the stream. I apologize, folks. This is what happens in live presentations. Sometimes there's some technical difficulties, but I promise there's some great content coming from here. All right, I'm getting the message that it seems to be okay right now. So let's go ahead and go back to this. So as I said before, if you're looking at the Rust subreddit on Reddit, it's common to see questions like newbie question regarding the borrow checker, help fighting the borrow checker, and does it ever get easier fighting with the borrow checker? However, as you watch people gain more experience in Rust, they tend to come around to the borrow checker and realize what it protects them from doing. So in answer to the question, is the borrow checker a friend or a foe? I say the borrow checker will become your friend through experience. And along with gaining experience with it, it's very helpful to understand how it works and why it does the things it does. We're going to dive very deep into that, but before we do, let's briefly cover who I am. I already went through this. I'm going to go ahead and skip it, but I will put my details back up at the end of the presentation. And let's get back to our overview of the Rust compiler. So here's the code that I want you to be looking at. And if we look at this Rust function, we see that we declare a vector composed of the integers 1, 2, 3, 4, and 5. And after it declares this vector, we use a for loop to iterate through each integer in the vector and print it out on a new line. If I run this with cargo run, as expected, I will see the numbers 1 through 5 printed out on the screen. Now this seems pretty simple. Cargo builds and runs this piece of code for us, but there is a lot that happens underneath the surface in the compiler when Cargo is building. There are 5 general stages to compiling a piece of code. It starts with lexical analysis of the code, then parsing of the code, semantic analysis of the code. This is where the borrow checker comes in, optimization of the code, and finally code generation, where the compiler creates that executable binary of our code. When we look at the stages laid out in a list like this, it might seem like they will run linearly. And in some compilers, they do. However, if you've delved at all into the Rust compiler internals, you might be thinking, wait a minute, Isn't the Rust compiler at least partially query-based rather than linear-based? And the answer to this is yes. It is partially query-based at this time, but that is out of the scope of this particular talk. For the sake of clarity, I'll speak to the internals of the compiler as if they were functioning linearly. However, if you want to delve more into how the Rust compiler is query-based and what that means, check out the guide to Rust C development for more information. This guide has been a big help to me as I have learned myself how to hack on the Rust compiler. So check it out and get all the information you want about the Rust compiler and more. Going back to the stages of compilation, let's start with the first one here, lexical analysis. During lexical analysis, a program within the compiler called a lexer takes the raw Rust source code, called a lexeme in this context, and analyzes it, and then splits the code into tokens to make it easier for the compiler to parse. And speaking of parsing, we go on to the next stage of compilation called conveniently parsing. And in the parsing stage, what happens is a program within the compiler called a parser takes those tokens created in the previous stage and analyzes them, and then translates them into an abstract syntax tree, or AST. Having the tokens in this data structure makes it quicker and easier for the compiler to do the rest of its work. And now, after it's done the parsing, the Rust compiler, before it moves on to that next stage of compilation, will take the abstract syntax tree generated by the parser and first expand any macros included in the code. If we look back at our original source code, print line, our line here, is actually a macro. So at this point, this line would be expanded to something that looks like this. This is what the full expanded print line macro looks like, and how it would be represented in the abstract syntax tree. The next thing the compiler does is it also desugars some of the syntactic sugar that makes writing Rust so delightful. For example, in Rust, the for loop is a piece of syntactic sugar for an iterator. If we were to desugar this section of code, it would consist of both a match statement and a loop. The functionality of this code is identical to the for loop in our original source code, but desugaring it like this makes it easier for the compiler to understand and optimize it. Something I like to say is sugared code is for the human who's writing and reading the code. Desugared code is for the compiler. And at this time, the compiler also resolves any imports in the code. So if you are bringing in an external crate or using internal crates or modules, those would be resolved here as well. And finally, after the compiler does all these things, it converts that abstract syntax tree into the higher level intermediate representation, or HIR. Some people say here, some people say HIR. I generally prefer HIR. So let's pause here and take a closer look at how that HIR is constructed. It helps to understand the data structures that make up the HIR. The first data structure is a node. This corresponds to a specific piece of code. This is identified by an HIR ID. And that node belongs to a definition. A definition is an item within the crate that we are compiling. Definitions are primarily top-level items within the crate. This is identified by a def ID. And that definition, defined by the def ID, is owned by the crate data structure. This is the crate we are compiling with Rust. This data structure stores the contents of the crate we are compiling and also contains a number of maps and other things that help organize the content for easier access throughout the compilation process. This crate is identified with a crate num. So looking back at our original source code, let's focus on this section here, that for loop. And remember that this loop desugars into a match statement and a loop. If we look at the node in the HIR that represents this match statement, we would see something similar to this. Now, this is a little hard to read for humans, so let's break it down. This arm structure represents a single arm of the match statement that our for loop desugared into. And then we have the HIR ID for this piece of code. This identifies a node that corresponds to that code within the HIR. And that node is owned by a definition. The definition is some top-level item in the crate. And that definition data structure is owned by a crate data structure. So our for loop is a node within a definition within our crate. And that's how we can identify where this node corresponds to in our original code. What also helps us do that is what is called a span. The span stores the file path, line numbers, and column numbers of the original source code. This will be very important in the future as we optimize and desugar the code. If we encounter a problem with the code, if the compiler encounters a problem after it is desugared and optimized, we still want to be able to show the user where in their original code that they wrote that the error was generated. If we were to have a problem with the desugar code and show them those lines, it probably wouldn't mean that much to them because it's different from the code they originally wrote. And at this point, the compiler then takes this HIR and lowers it again into the mid-level intermediate representation, also known as the MIR. The MIR is constructed as a control graph. The units within this control graph are called basic blocks, which are identified with values like BB0 and BB1. Within these blocks, each has a sequence of statements that execute in order. The very last statement is known as a terminator. This is where we get the go to another basic building block. And this is how the program proceeds throughout its structure. Now, this is a pretty simple example. There's only one direction the basic blocks can go. But if our code had an if-else statement, like this, where we have a condition, if that condition is true, we do one thing. If it's not true, we do something else. The control graph would look like this. The terminator of BB0 would have the option to either proceed to BB1 or to BB2. In this case, there is more than one path within the program that it can take when it encounters a terminator within a basic block. If you are curious about more about the MIR, there are definitely more data structures involved in it. Again, check out that guide to Rust C development for more information. Let's go back to our desugared code. And let's take a focus on this match statement, which is assigned to a variable called result. If we looked at the MIR for this piece of code, it would look similar to this, and I have simplified it for the sake of appearing on a slide. Up here in the top left, you can see we have our basic block, which in this case is identified as BB2. And then we have what is called a local. A local in the MIR represents a place in memory, or more specifically, a place on the stack frame. In this case, _5 corresponds to the value of the variable result. And like in the nodes in the HIR, we have a span, the piece of the original Rust source code that each node in the MIR corresponds to. Again, if we encounter an error when we're operating within this MIR, we can still easily refer to what lines in the original source code caused the error. And that brings us to this third stage. And this is big in the Rust compiler, semantic analysis. This is where the compiler tries to figure out what the program is trying to do in a way the compiler can understand it and then translate it into machine code. And at this point, after it's lowered the HIR into the MIR, the compiler will run several checks on the MIR, including the borrow checker. Now we're going to come back and dive deep into the borrow checker in just a few moments. But for now, let's focus on these last two stages of compilation, optimization and code generation. These stages are where the code is transformed into an executable binary. In the Rust compiler, we use LLVM to do this for us. LLVM is a commonly used collection of modular and reusable compiler and toolchain technologies. The Rust compiler uses it to further optimize the code and generate the machine code to run it as an executable. Before it uses LLVM, the Rust compiler takes the MIR we created earlier and lowers it into the LLVM intermediate representation, or LLVM-IR. And the LLVM-IR is pretty unreadable to humans, but it looks something like this. As we can see, the LLVM-IR is still constructed as basic blocks, like in the MIR. And after this, the compiler then uses LLVM and takes in that LLVM-IR that we created, and then it runs more optimizations on it and emits machine code. And it then links the machine code files together to produce the final binary. And this means when we run our code with cargo run, we see those numbers printed out. So yay, that gives you a bit of an idea of how the compiler works to take your Rust source code and make it something a computer can execute. And at this point, I do want to go back and take a deeper look at the borrow checker. And for that, let's use a different piece of code. If you are looking at this code, if you're reading it and thinking this will error out, you are right. And we'll see how and why that happens in just a moment. First, we declare the variable x and give it the type of string. Then we set the value of x to the string high rusty days. Then we say that the value of y is equal to the value in x. And then we attempt to print both variables. If we were to try to build this piece of code as it is now with cargo build, it would give us an error. And this error is the result of the borrow checker. We are trying to use a value, or we are trying to borrow a value after it has already been moved. Let's go through how the borrow checker identified this error. The borrow checker does several things, including tracking initializations and moves. How this plays out in our code is when we start with this first line, where we declare the variable x to have a type of string, x is not actually initialized at this point. It won't be considered initialized until it is assigned a value. And if we look at the MIR for this line of code, we can see that x is represented by the local _1, and local _1 is assigned the type of string. So this is the MIR that corresponds to this line of code, and this is what the compiler is analyzing. Now let's look at the next line, where we create the high rusty days string and assign it to be the value of x. Now that x has a value, it is considered initialized at this point. So x is initialized and the borrow checker is aware of that. To do this, we create a new place in memory, local _2, where we store the high rusty days string. And then we move the value stored in _2 to _1. Remember, _1 corresponds to the value of the x variable. So we have created the string in memory and moved it to be the value of x. Now let's look at this line, where we attempt to create the variable y and assign it the value of x. This line is where the value of x is moved to y. It's not duplicated, it's moved. If we look at the MIR created for this line of code, we see that y is assigned to the local _3. Remember, a local represents a place in memory or a place on the stack frame. And _3 is given the type of string. Then the value at _1, remember that represents the value of x, is moved into the value of _3, which represents the value of y. This means when we get here in our code, when we try to print x, we try to print the value of x. X is not initialized at this line, so we cannot print it. Once that value is moved, x is no longer considered initialized. And that's what generates this particular error. We're attempting to use the value of a variable after it has been moved. And something I'd like to specifically call out is how the compiler shows where the error was generated from the original source code. This is that span that is attached to all the nodes of the HIR and the MIR. So even though we had lowered this code into MIR, or mid-level intermediate representation, we still tracked what items in the MIR corresponded to what places in the original Rust code. And this is very helpful to the end user. What is also helpful is this. The Rust compiler not only tells you what the error is and where it is, it gives you a command to get even more information about the error so you can fix it. And let's go ahead and run this command. If we run this command, we see not only an explanation of the error, but also a piece of example code that would generate it. Then the message gives you even more information, not just about what the problem is or where it originated, but how to fix it. This suggests using a reference to borrow a value rather than attempting to move the value, which is what we saw done in the MIR representation of our code. So let's do what this says. Let's take this advice and change this line so that y is assigned to a reference to the value of x rather than moving the value of x into y. And let's go ahead and run this again. And once the compiler builds the code and executes it, we see the message, "Hi, Rusty Days," printed out twice. Rather than fighting the borrow checker, we used it to make our code even better. Along with tracking initializations and moves, the borrow checker also deals with lifetime inference. And let's go over exactly what that means. Rust uses the word lifetime in two distinct ways. The first way is to refer to the lifetime of a value. That's the span of time before the value of the variable gets freed. Another word for referring to the lifetime of a value is referring to the variable scope. And let's see how this plays out in our code. And let's start with the second line, where we assign the value of x to this "Hi, Rusty Day" string. At this point, x is live. It's initialized. Its lifetime begins here. When we get to here and move the value of x into y, this is the end of x's lifetime. And that means when we get down here and we try to use x again with our uncorrected code, x is dead. Its lifetime is no longer in effect, and it is no longer initialized. This is why this program generated the error that we saw. The other way Rust uses the term lifetime is refer to the lifetime of a reference to a value. This is the span of code or span of time in which the reference can be used. Let's look at that corrected code where we created a reference. So here we assign the value of y to be a reference to the value of x. If we look at the MIR for this line of code, we remember that the local _1 refers to x, and the local _3 refers to y. And we see that _3 or y is assigned a reference to the value of _1 or x. This is how creating a reference looks in the MIR. And this is what the compiler is analyzing with the borrow checker. Looking back at our code, let's alter this slightly. And let's try to drop the value of the variable x before we try to print out the value of y. So we're dropping the value of x here. If we do this, and then try to build our code with cargo, we will get another borrow checker error. We cannot drop x, we cannot move out of x because it is borrowed and that borrow is used later. The borrow checker tells us that x, because it is referenced by y, needs to stay alive for at least as long as y needs to stay alive. That means x's lifetime must be greater than or equal to y's lifetime. Looking at this in the code, again, this is x's lifetime. This is the lifetime of x. And this is what needs to be the lifetime of y, which is a reference to x. Notice that even though these two lifetimes overlap, x's lifetime ends before y's lifetime is supposed to end. That means that once we drop the value of x, again, x's lifetime is over, and y can no longer reference the value of x after this line. So at this point, in this last line, x would be dead, its lifetime is no longer in effect, and y would not be able to reference it. Again, in order for this code to compile, the lifetime of x must last at least as long as the lifetime of y. And how these two ways, the overarching way the scope and the lifetime of a reference relate to each other, is that if you make a reference to a value, the lifetime of that reference cannot outlive the scope of the value. This is something that gave me a lot of trouble early in my Rust days, and once I understood how it worked, it made it much easier to do my Rust. Now, as I move toward concluding this presentation, I want to make sure that you know that there is so much more to the Rust compiler and the borrow checker. Again, if you want to know more, check out the Guide to Rust C Development for more information. It is a fantastic resource. It has been so helpful to me as I've taken my own steps, not only into using Rust, but hacking on the Rust compiler itself. Going back to this question from the beginning, is the borrow checker a friend or a foe? My answer is it's a friend, though a very strict friend. But the best thing about this friend is it will not only tell you when you do something wrong, it will also tell you how to fix it. And I find that to be one of the best qualities I can find in a friend, as well as one of the best qualities I can find in a compiler. Thank you. There is my information again if you want to reach out to me, and I'm ready to take some questions. All right, I see that we are waiting for questions. Certainly hope this is helpful to you. It's been helpful to me just creating this presentation. All right, just so you know, if you're watching at home, there is a little bit of a lag. So if you see me just standing here, that's because I'm waiting for the broadcast to catch up with the lag, and I'm looking forward to your questions. right, sure anyone out there doesn't have questions? I know I had a lot of questions about how the compiler works when I got started, or questions about the borrow checker. You can ask questions about This Week in Rust if you like. All right, Twitch user CRD477 says, thanks for the talk. You're welcome. Rust's ownership model seems to be pretty unique in the PL world. I'm assuming PL means programming language. Has anything like it been tried in previous languages? Well, the answer to that is I don't know. I don't know of any ownership models in the programming language that I've used, at least, that come anywhere close to Rust. In my experience, Rust is pretty unique, at least as it comes to mainstream programming languages. So if anyone knows of programming languages that use Rust, an ownership model similar to Rust, please go ahead and send it to me. I'm curious. All right. Next one is from Twitch. Uwedrache, Uweddrache, asks, is X's lifetime extended by being borrowed by Y? And the answer to that is no. X's lifetime will end when we drop it, even if it's borrowed by Y. The nice thing about the borrow checker is, as you saw, that prevents us from trying to compile the code when X's lifetime runs out before Y's. Next question from Damien on YouTube is, did you have any bad habits from other language that made borrow checker unhappy? If so, what were such habits? Yes. I came from the Ruby world, like surprisingly a lot of people in the Rust world. So I was very used to duck typing. I was very used to not really paying attention because I had the garbage collector to when my variables went into scope or out of scope. So breaking those habits was hard. It definitely took a few months, but it now feels like the Rust code I write is so much safer than the Ruby code I wrote, or the C# code I wrote before that, JavaScript, etc. So I really like Rust. Let's see here. Cage from YouTube says, would you recommend some techniques like RCs or ECS? I'm not entirely sure what you're referring to like that. RC might mean ref cell, but I'm not sure what ECS stands for. So if you don't mind, if you clarify that, I'm happy to come back to the question. And all right, so someone from Twitch, Mr. Edmakes, says, in your last example where the lifetimes of X and Y overlap, do you know why it was decided to be an error as opposed to having Y take ownership? And this is something that has been brought up a lot. I actually, in the issue of This Week in Rust that is going out later today, someone writes, Boats, who's a Rust community member, writes an article about what would it be like if we had a smaller Rust. And I believe it's in that article that he covers what if we could have, if lifetimes of X and Y overlap, why couldn't Y take ownership? And the answer to this is I'm not sure. I know it was a decision made early in the Rust process. I can probably find the RFC that explains it, and I will try to do that after this talk and tweet it out. Next question is from Parker McMullen on YouTube. And they say, do you ever see a future where the borrow checker moves from helpful compiler hints to being more abstracted and inferring what the programmer meant to do while still staying optimized? I could see it if we made a good case for it, if we did not have to give up any of the safety mechanisms that are in Rust right now. The reason so many people love Rust, especially when they come from the C++ world, is they feel very safe because they know the compiler will tell them when something is incorrect. As for the compiler abstracting and inferring what the programmer meant to do, that'd be very interesting. I'd love to see a prototype of that. I don't think the Rust language will move to that anytime soon, but if someone can make it work well and make a good case for it, and the rest of the community agrees with it, or at least the rest of the core team, I could see us trying that. So if anyone's interested, if anyone wants to build a prototype, please do. I would love to see it. Next question on Twitch. Chekofif, I'm not sure if I said that right, but said, has there been any research into whether the borrow checker has produced measurably more reliable code? The answer to that is I believe there has been formal research into it. And I don't know if it counts as formal research, but Microsoft wrote an article, I think Google's written articles too, about why they are rewriting their C++ code in Rust. A lot of times I see in the Rust channels and Slacks that I'm in that people ask, well, couldn't what Rust does just be done by C++ programmers who are committed to good standards and writing safe code and really experienced? And the answer to that is the thing about programmers, as you all know, is we're all human. We all make mistakes. I tell people about the time I wrote some not optimized Ruby code, and I ended up DDoSing myself because the database queries it was trying to do weren't optimized. So yes, I believe there has been some research. The best response to that I have is we have big tech companies who have been using C++ for a very long time who are seeing the value of Rust. All right, Jeff from YouTube asks, how do things change when you add lifetimes? And the answer to that is lifetimes are, even though I've been doing Rust for a few years, and I'm assuming you mean lifetimes put within the arguments of the function, or specifically noted lifetimes. And that, I mean, it would, if you denote that the lifetime of X had to be as long as the lifetime of Y, there might be a way to do that with specifying lifetimes. And that would mean that X would not be uninitialized, I believe, when you try to use Y. So that is another potential way to solve the problem we saw in our code, would be to add a specific lifetime into it. Next question comes from YouTube, Bartolomé. I sincerely apologize if I'm butchering the names here. How much would borrow checker and borrowing be affected by Chalk and Polonius in the near or not so near future? That is a great question, and I think that's something that's still being figured out. When I started putting this talk together, I worked with Nico Matsukis at Mozilla, who's on the Rust core team, and I told him I'm putting together a talk on the borrow checker, and he said, oh, let me send you my talk about Polonius. So Polonius would change things. Chalk would potentially. I'm not as familiar with Chalk as I am with Polonius, because Polonius at least takes a different approach to tracking borrows, lens, etc. So I will tweet out a link to Nico's slide deck, which will go into more detail about Polonius. Next question from Chekhov. Do people working with borrow checker find this has changed how they think about the systems they build? Any anecdotal thoughts on this as someone who's been using it for a while longer than the rest of us? Yes. So I did take computer science courses in college, but I was not a computer science major. So I learned most of my programming from doing it. And I started with web programming. And with web programming, yes, memory is a consideration, but when you're not doing back-end system programming, you don't consider it as much. Now that said, before I was at Mozilla, I was at Chef Software, as you can see in the photo that's accompanying my details on the slide. And that was the first time I was dealing with back-end systems code. And I ran into a lot of trouble trying to do it in languages like C++ or something. And part of that was inexperience. But when I found Rust, it forced me to think through ahead of time of how my program would interact with memory and how the scopes of my variables and such would work through. And it's very much, I think of Rust as, someone has said this, I don't remember who, is compiler-driven development. So I write some code, I try to build it, and I see what the compiler tells me, and then I try to correct my code, and I go back and forth and iterate on that. So yes, it has made me think a lot about the systems that I build. Next question is Michael Ward. Which of the upcoming changes to Rust are you and/or Mozilla most excited to see? I can tell you one I'm working on personally, which is adding the ability to use a stream with async, or adding the stream function of async code into the standard library. There are external crates like Futures RS that allow you to use a stream. So you can kind of, it's like an iterator, but for async code. But we want to move that into the standard library. So async is an area that has a lot of my focus right now, and it works well the way it is, but I can't wait to innovate on that. I'm working on drafting an RFC now regarding moving the stream trait into the standard library. So async streams, I would say, is what I am personally most excited about right now. Michael Lazowski asks, how do you rate the Rust community comparing to Ruby? Well, most of my experience with the Ruby community was, 5 or 6 years ago, and there's a lot of people who migrated from the Ruby community to Rust, like Steve Klobnik, Sean Griffin, etc. So it feels like a lot of the community leaders are the same. I would say what I love, Ruby community is very good. What I love the most about the Rust community is that we are a community that considers empathy and personal maturity to be as important as technical excellence. And Ruby community has some of that, but other technical communities I've been into, that is definitely not the case. And it is wonderful because it helped me learn Rust, and to see how other people learn Rust, how they grow, and the power of the things they create. And a lot of that is fostered by the Rust community. So I rate the Rust community very, very high. Let's see here. Next question. Ethan Brearley. How much do extra checks Rust does affect, I think you meant compilation performance. I'm not sure, actually. So let me get back to you on that one. ECS means Entity Component System. Answer to that is I don't know. I'm not as familiar with those systems, I think, but I'm very curious. Michael Ward on YouTube asks, are there any known borrow checker improvements that will vastly improve ergonomics like non-lexical lifetimes did? I am sure there are some in the works. I don't know of any specific ones off the top of my head right now. S. Burnham on Twitch asks, since Rust doesn't have a RPL, do you find new Rust stations often use the compiler as a testing mechanism, i.e. attempting to compile, fix, compile again? Is there a better way to experiment in Rust? Well, I can tell you when I was in the Rust station, that is exactly what I did. I would write a small piece of code, see what the compiler did with it, compiler errored out, I would change it, and I would make the compiler be able to use that small piece of code before moving on to the next one. That honestly for me has been the best way to learn. The best thing about the Rust compiler, and someone will be doing a talk about this at RustConf in August, is that the compiler itself is a tutor. It's an automatic tutor, and the error messages are very helpful because, again, they not only tell you what was wrong, they tell you how to fix it. So I would say as a new Rust station, yeah, go ahead and compile, fix, compile again. For me, that was the best way I could learn. And I know it's frustrating. I promise it gets better as you come to understand why Rust does the things that it does. Guliharm Souza on YouTube says, when my code starts to be inundated with explicit lifetimes, I usually stop and rethink my types and logic. I take it as a hint from the language that my code is bad. Do you share this experience? I would say I do. When I'm putting in a ton of explicit lifetimes, I kind of feel like I'm flailing against the borrow checker rather than really using it to understand why it does what it does. So yes, a lot of explicit lifetimes in a small amount of code, that tells me there's probably a different way that I can structure it. And as you say, stop and rethink your types and logic. What I would also suggest doing is, pause, obviously read the compiler error messages. And if you're trying to do a lot of explicit lifetimes to correct that error message, Google the error message itself. There's a lot of stuff on Stack Overflow. I believe it's Rust community member Burnt Sushi. I love that name. Has posted so many really helpful answers on it. And the best thing about Burnt Sushi's answers is they very clearly understand how the Rust compiler works, and they give answers along those lines. So that's the other thing I would do is, yeah, it's a sign that something you're making your code more complicated than it needs to be, and use the compiler for help with that, and also use the web resources. Let's see here. Jeff Barszewski says, will your async streams support back pressure? That is something that we are talking about right now. I'm still working on the RFC in conjunction with the async working group. So as the RFC is now, remember this is still in early stages, it has not been formally proposed yet. I don't think we'll support it in the initial implementation, but it is possible that could change before we open the RFC and even after the RFC is open based on the response of the community to it. So stay tuned, we are definitely talking about that. And let's see here, Mike Lasowski says, have you read Computer Systems, The Programmer's Perspective? If not, I would think it would be interesting for you. I have not read that, and that sounds fantastic. So I will give that a read, and if anyone else wants to form a book club or something over Twitter or over Zoom to read it, let me know. All right, last question we have right now. Votek Polak says, what do you think about Verona from Microsoft? I'm not familiar with Verona from Microsoft, so I will have to check that out and get back to you. Any other questions before we close? All right, so looks like that's all the questions. So I am going to, let's see here, pick a question, pick the most interesting question. These are all interesting, this is hard to get that code for a Manning book. Let's see here. I'm going to go with Guli Haram Souza. Let me put that name because I'm probably butchering it. I apologize profusely. In my chat with the organizers of Rusty Days. All right, well, enjoy your code from Manning, and thank you everyone so much for tuning into my presentation, and I am hoping to eventually see you all in person again.